because the recording stopped. I hope it doesn't happen in the middle when we have started. Okay. So the exam is online, it's ongoing. Okay, you can still take the exam until tomorrow noon time, no? Okay, do you follow? So for today, we will introduce a new topic. If you look at our new topics, we will be going into hardware in a short while, no? So we'll be discussing Boolean algebra and logic gates. And there's already a practice test that's ongoing. Do you follow? No, a practice test on Boolean algebra. Okay. You can pass your solutions later, no? I will show you that later, and I will discuss that. No? And then we will have computer hardware. Okay, after Boolean algebra, we will have computer hardware, and then we will have a formative test number 3. Okay, most probably this is in the middle of October. Okay, formative test number 3. Okay, in the middle of October, and our last topic will be computer programming, HTML and computer programming. Okay, I hope we can also discuss other topics like SQL, no? But certainly we will discuss web development, no? Computer programming using JavaScript, and we will also discuss HTML, no? And you will launch your own web page, no? In the net. Okay, for in my case, I am using W3 School Spaces, no? Which is currently newly launched this year, no? It's a free site and a free domain which you can use to launch your website. You can use any other host if you like, as long as you email me the correct URL address. Okay, any questions so far? So our next formative test will be on logic gates and computer hardware. Okay. So we will start logic gates today. No? You can download the slide. You can look at the crash course, no? These videos. You take a look at this, and then we are going to use a simple software for constructing Boolean circuits. It's called CIDAR Logic. You can look at the video on how to use. This is a very elementary software. This is a toy software, no? Which engineers use to make simple circuits. Okay, you can download this and introduce and use this in our exercises. Okay, for the moment we will discuss logic gates and Boolean algebra. This is a continuation of Boolean math, no? Okay, Boolean arithmetic. I have a local copy, so we can. I can. Okay. Any questions? Can we start now? I'll call the roll later again. So you can download the slide. It's in our site. Logic gates and Boolean algebra. Okay. Logic gates are the continuation of Boolean arithmetic. They are used to implement Boolean arithmetic in hardware, in a computer hardware or in an electronic hardware, no? Which means like a calculator, no? A cell phone, whatever you have. No? So logic gates are electronic circuits that are used to construct digital systems like your calculator, no? Your computer, scoreboards in basketball, no? These are digital systems that process digital numbers or Boolean numbers. They are constructed using basic logic gates. There are 3 basic gates. Why is it called a gate? Because it's actually like a gate valve, no? Like a faucet when you turn it on and off. No? It's based on transistors, okay, which are controlled like faucets, like gate valves in a water system. You have pipes, no? You control flow of water by using gate valves. Okay, this time we control output or generated Boolean values using logic gates. Okay, they're termed from gate valves, no? In a plumbing, no? in a plumbing scenario, no? You follow? But this time we are not doing any plumbing, so we call them logic gates. Okay, the very basic is AND. So usually in a circuit, no, An AND gate is represented by a schematic symbol. This is the schematic symbol in a circuit. No? Have you done electronics before? No, you do schematics. A schematic is a drawing of an electronic circuit or an electrical circuit. So any gate, like since it's a gate valve, will have an input and output. Okay, it's represented as a curved rectangle where one side is curved, the other side is sharply straight. Okay, you can invert the drawing. The sharp straight side is the input side because it has a function. No? The gate has a function, and being such function, it will have an input and will have an output. Okay, so in a schematic symbol, we label AND with a curved rectangle. One side is curved. The curved side indicates the output side. We mean this A and B. By this, we mean A and B, which means the function being done is A being ANDed with B, or AB, or A times B. Sometimes it's A dot B because AND signifies Boolean multiplication. Okay, ANDing is like multiplying. Do you follow? We'll find that out later. No? An OR gate. Okay, an OR gate is another basic gate where both sides are curved, but the input side is not pointed. The output side is the pointed curve, like this, like a tip of an arrow. Do you follow? No? So this signifies A or B. Sometimes it's written as A plus B because the OR operation is actually an addition. Do you follow? Okay. We'll find that out later. OR and plus are the same. No? It's a Boolean arithmetic plus. Okay. Any questions? The NOT gate, or called an inverter. The NOT gate will invert the input. So if A is 1, the output is 0. If A is 0, the output is 1. Okay. So it's also called the inverter. Okay. Or the complement. No. One's complement. Okay. An inverter is like a one's complement. Sometimes it's written with a bar inside, above, or a tilde before, no, or a quote after, a single quote after. No? Okay, I'll call the roll later. No? So there are other logic gates. These logic gates are a combination of the basic gates, like the NAND gate. The NAND gate is an AND followed by a NOT. So NOT AND. Okay. So NOT AND is the complement or the one's complement of an AND. Okay. We'll describe the behavior of these gates later. No? Okay. NOT AND or NAND. So we also have an OR. So an OR followed by an OR. Okay. So an OR is inverted, becomes an OR. Okay. An AND, when inverted, becomes an AND. Okay. Any questions so far? Any questions? Huh? Just the whole thing. The function of okay. So there's another gate called EOR gate. It's like an OR. It's also called XOR. EOR for exclusive OR, or it can also be called XOR or EOR. No? It's an exclusive OR gate. It's like an OR gate with a difference in a certain set of inputs. No? So 1-1 sila magkaiba. Okay. So the sign, how different is an XOR from an OR? We will describe that shortly. No? So the sign is a plus covered by a circle. No? It's an exclusive plus. We'll find out why it's exclusive. What did it exclude? Okay, we will find out. There's a summary of all the symbols. This is an AND. This is an OR. So A times B, an OR is A plus B. We have a NOT of A. We have a NAND of A times B. We have an OR of A plus B, and we have EOR of A and B. Okay, or exclusive OR. Now, another way of representing a logic gate is in terms of a truth table. Okay, the truth table describes the behavior of the logic gate. What will it do? What kind of processing will it produce? Okay, For example, we have a summary of all the truth tables of AND, OR, NAND, NOR, EOR. Okay, do you follow? A truth table is not a table of truth. Okay, it's a Boolean truth. No, Boolean truth. It's a mapping. Can you map the truth? Of course not. No, but you can map logical truth or Boolean truth because Boolean values are limited to only two types of values like 0 and 1. No? So we can map. So a truth table is a list down of all possible inputs and their corresponding output. No? So it describes the behavior of a logic gate. Do you follow? For example, we have the AND truth table between A and B. When you say A and B, when A is 0 and B is 0, AND is 0. That's the truth. One that's part of the truth. No? 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1, which means that for an AND to be successful, both A and B should be 1. Okay? When one of the inputs is 0, the AND will fail, which means that the AND will output a 0 if at least one of the inputs is 0. Do you follow? Do you follow? So the truth table for OR. Now, how do you generate the rows of a truth table? You do a binary count. Okay? 0, 0, 0, 1, 2, 3. Okay? Because 1, 0 is 2 and 1, 1 is 3. Do you follow? We generate a binary count to generate the rows of a truth table. Any questions so far? So the truth about the OR gate, 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. And 1 or 1 is 1. So take a look, no? If at least one, in an OR gate, if at least one of the inputs is 1, the output becomes 1. So it's like the opposite of AND, where when one of the inputs is 0, automatically the AND becomes a 0. In the OR, when one of the inputs is 1, the OR becomes a 1. When both are zeros, the OR becomes a 0. You follow? So that's the logic of an OR. Okay? When you say boy or girl, it doesn't matter. Because if one of them is a boy or one of them is a girl, or both of them are boys and girls, that's an OR. But when you say boy and girl, both one of them should be a boy and one of them should be a girl. Okay? Do you follow? Diba? Boy and girl, hindi pwedeng two of them are boys. It cannot be that two of them are girls or none of them are boys or girls. Diba? Do you follow? So it's like the logical truth, no? Logically it follows, no? NAND. NAND is the complement of AND. When AND is 0, NAND is 1. Okay? When AND is 1, NAND is 0. Okay? NOR is the complement of OR. When OR is 0, NOR is 1. Do you follow? So when we say, when at least one of the inputs is 1, the NOR becomes automatically a 0. Okay? What's an EOR and an exclusive OR? The main difference between an EOR and an XOR is an EOR or OR is in the last. No? One EOR 1 is 0, which means exclusively one of them should be a 1, but not both. Do you follow? A and B should be a 1 of them, but not both. When both are 1s, EOR will output a 0. Do you follow? Strictly boys and girl. A boy and a girl, strictly. Hindi pwedeng both boys and girls. Okay? Do you follow? Okay? Do you get my point? The difference between an EOR and an OR. Okay? Do you follow? Now, if you have more than one input, no? You count the ones. If the population of ones is odd, like 1 or 3, okay, the EOR will output a 1. If the population of ones is even, the EOR will output a 0. Okay. So whether it's an even and odd terminator. Okay. Any questions? Okay. So what are the properties of a Boolean truth table? One of them is called the number. Okay. When you say the number of the truth table, we refer to the number of rows or tuples that are part of the truth table. Now, the number of the truth table is dependent on the size of inputs or size k. If the input size is k, the number of rows is b to the k. B means 2, 2 to the 3. For example, if there are two inputs, so A and B, there are two inputs, right? A and B. So the number of tuples is 2 squared or 4. If there are three inputs, A, B, and C, the number of rows will be 8. If there are four inputs, A, B, C, and D, the number of rows will be 16. Okay? Do you follow? So what do we mean when we say the number of a truth table? The total number of rows that can be generated in the truth table. And it can be computed as B to the K, where K is the number of inputs. So when there's AB, the number of inputs is 2. A, B, and C, the number of inputs is 3. A, B, C, D, the number of inputs is 4. Any questions so far? No? Simple, no? Another property is called a min term. It's a product term. It's like in algebraic expressions. No? A term is AB is a term. A times B is a term. AB plus XY, okay, is a sum of terms. Okay? Do you follow? Do you follow? AB plus XY is a sum of terms AB and XY. Okay? A min term is a product term that has all variables, okay, present and correspond to 1 in a truth table. We'll have an example, okay? A max term is a sum term that evaluates to 0. Sum siya. So it's not, min term is a product term, so it's an AND. A max term is a sum term, so it's an OR. Because a sum is an OR and a product is an AND. The multiplication kasi is AND and addition is OR. Do you follow? We'll have an example. No? Boolean functions is a mapping of k-bit strings. So that's the truth table. No? It's a mapping of k-bit strings to values either 0 or 1, which is the output. Okay, here's an example. No? So this is a truth table with two variables. The number is 4. Why? Because 2 squared is 4. So 0, 0, 0, 0, that's the first row. To generate the rows of the truth table, we do a binary count from 0, 0, 0, 1, 2, 3. Do you follow? Do you follow? Okay. So for example, we have a Boolean function y equals ab plus a not b. So ab is 1, 1. A not b is 1, 0. Okay, that's why it's a 1 here. All the rest are zeros. No? So this is a min term. AB is a min term. A not b is another min term because they are products. Okay. So if you look at this, what are the min terms in this truth table? These two rows. The two rows that evaluate to 1 are the min terms of the truth table. They follow? If you write them in a function, there are two min terms, AB and A not B. Okay. They are min terms because they contain all the variables A and B, whether complemented or not, and they evaluate to 1. Now, 0, 0 or not A and not B is not a min term because it's 0. Not AB, which is 0, 1, is not a min term because it evaluates to 0. Okay? Any questions so far? No? So, pag makita, if you see the truth table, you will know which are the min terms. Okay, these are the min terms, those that evaluate to 1. So this is a min term AB because this is 1. A not B is also another min term. Okay. So there are standard forms to write a Boolean function. No? Canonical, which means it has been standard for a very long time. No? Even before we were born, before your parents, 1950s, no? 1960s, no? Because the first came up was invented in 1963. Okay, what are the standard forms? The sum of products. Ito, sum of products. Where each part is a term, no? So the sum of bin terms, SOP, sum of products. This is the first way to write a Boolean function. Okay, y is equal to AB plus A not B. This is a standard form called the sum of products, which is the sum of all min terms. Okay, by adding all the min terms in the truth table. Okay, do you follow? We can also write this as a product of sums by multiplying all the max terms in a truth table. What's a max term? A max term is a truth table, is a row in a truth table that evaluates to 0. So these are the min terms, these are the max terms. Okay, do you follow? So another way to rewrite this is quantity A plus B times quantity A plus not of B. Okay, this is a product of sums canonical form. Y is equal to AB plus A not B is a sum of products canonical form. No? Canonical, when we say it's been a standard for a very long time. Okay, canonical na eh. No? It's a canon. Okay, it's in the canon law. Okay, of arithmetic. Okay, any questions? Another way to write a truth table is in terms of a map. It's called a K-map. It's called a K-map for the inventor Maurice Carnot. No? The inventor is the mathematician Maurice Carnot. American, no? I don't know, but it comes from another university. No? Maurice Carnot invented the Carnot map or the K-map in 1963. It's another way of writing a truth table. It's writing a truth table in terms of a grid. No? A truth table is a table, a K-map is a grid, where variables are assigned to either rows and columns. Okay, do you follow? So this is the truth table. This is the equivalent K-map or Carnot map. So if you look at that, 1, 0 is, this is 1. A is equal to 1, B is equal to 0. So there's a 1 here. There's also a 1 here. A is equal to 1 and B is equal to 1. This A is equal to 1 and B is equal to 1. So there's a 1 here. All the rest are zeros. Okay? Do you follow? So in a truth table or a K-map, whether what representation you are using, you can easily look at the min terms and the max terms. No? Do you follow? Depending on your preference, which one is more appropriate? Doesn't matter. No? In a truth table, these are the min terms, the max terms. No? In a K-map, these are also the min terms, the grid values of 1, and the max terms are the grid values of 0. Any questions so far? No? Min terms and max terms. SOP, sum of products. POS, product of sums. Okay. Now we do Boolean algebra. The laws of Boolean algebra. How do we simplify Boolean expressions? Why do we need to simplify Boolean expressions? Now, if you have a polynomial, you simplify a polynomial, right? Why do we need to simplify Boolean algebra? Because we make them, we're just not using them as functions. No, we will convert them into switches or into circuits. Okay, the more complicated the function results to a more complicated circuit. No? A simpler function is also a simpler circuit. No? So a circuit is like a program. The more complicated it is, the harder it is to maintain. Okay, do you follow? So we will usually basic laws of Boolean algebra will be implemented as switching devices called logic gates. We will use Boolean algebra to simplify logic gates. A network of logic gates allows us to manipulate digital signals, like perform mathematical or numerical operations, perform translations. No? Do you follow? From one binary code to another. No? The scoreboard in a basketball court, no? That has Boolean functions. No? A Boolean variable can take two of the, what's the range of a Boolean variable? 0 or 1 lang. No? Unlike in a normal algebra, you can have a lot of range. No? 0 or 1 can also be used to stand for true or false, or T or F, or high or low, or on or off. On for true, off for false. Okay. Boolean operations transform Boolean variables. No? So Boolean operations will transform them into the desired form, no? the desired function. So the basic operations are not, and or. No? So it has also a sequence, no, and a hierarchy of operation. In math, you have MDAS. No? In Boolean algebra, you have NAO, not first before and or. Okay, not is the highest priority, followed by and, followed by or, except if they are enclosed in parentheses, which alters the sequence of operation. Okay, we can make more complicated Boolean functions from the basic Boolean phrase. Okay, how do we derive canonical forms? From given a truth table, how do you derive the min term form and the max term form? Okay, there's the process. To derive the min term form, if the value of the truth table is 1, take the normal form. If the value of the truth table is 0, take the complemented form. Here's an example. No? There is the value, the normal value is 1, 1. So we take A, B, that's the normal form. If the value of 0, like A, 0, 0, we take not of A and not of B. Do you follow? Not sometimes is tilde before the variable. So we have A0 and B is equal to 1. So since A is 0, we say not of A. And since B is equal to 1, we say B. Now for A is equal to 1, B is equal to 0. Since A is 1, we say A. And since B is 0, we say not of B. That's what we mean we say, if the value of the truth table from the truth table is 1, take the normal form. If the value of the truth table is 0, take the complemented form. Okay? Do you follow? So, for example, we have this here. Now, these are the min term forms. And we exclude those which are 0. So, we have A not B and AB. This M2 and M3. This min term 0, min term 1, min term 2, min term 3. Okay, because this belongs to row 0, row 1, row 2, row 3. That's all that what it means. Do you follow? No? So, ang min term dito itong dalawa. Do you follow? Okay. How do you derive the max term form? It's the opposite. If the value of the from the truth table is 1, take the complemented form. Okay, I'll check the attendance later. No? Again. To this. If the value, so baligtad tayo, if 1 complemented, if the value of the truth table is 0, take the normal form. Okay, baligtad. So, for example, in the max term form, A is 0, so we take A. Baligtad, no? B is 0, we take A plus B. A is 0, we take A, and B is 1, we say not B. It's the opposite of the term. But this time we use a plus. Okay? So we say capital M of 0, this is max term. Capital M of 1, these are the max terms. No? Do you follow? So the min term and the max terms are duals. They're like twins. They're one and the same. No? They are just in the different form, but they're one and the same. Okay. So for example, the sum of products is AB plus not A not B. And the max terms is A plus B times quantity A plus not of B. They are the same thing. You follow? The first form is sum of products or min term form. The second form is product of sums, which is max term form. Okay. Now in mathematical language, we say summation of M2 and M3 because they belong to rows 2 and 3 in the truth table. Sigma means summation. Phi means multiplication of capital M0 and capital 1 because they belong to rows 0 and 1 in the truth table. Do you follow? Do you get my point? M0 is A plus B, M1 is A plus not B. Like M3 here is AB, M2 is A not B. Okay? So are we getting here? So anyway, who's present? Landitzo and Q. Did I miss anyone else? Any latecomers? Yup. And Simon? Yeah, Simon. Yup, he's already there. Simon just came in. Did I miss anyone else? Just chat me, okay? I only saw for the moment. Mabano? Yeah, no problem.
Excuse me, sir.
Yes.
Si Narca po is absent po. Nag-second dose po siya sa vaccine.
Okay, thank you. Narca. Ito. Second dose. You just take note. Okay. Any other? We'll proceed now. So we know sum of products and product of sums, min terms and max terms. Okay. They're one and the same. The laws of Boolean algebra. They're used to simplify Boolean expressions. No? Like in simple algebra, we have commutative law, which means that of addition and multiplication, which means that when you do addition and multiplication, the position of the variables are intercommutative. You can change position. That's not where you start. X plus y is equal to y plus x, or x or y is equal to y or x. X times y is equal to y times x, or x and y is equal to y and x, because multiplication is and addition is or. Do you follow? Associativity law. When you do addition and multiplication of several terms, it doesn't matter where you start. Quantity x plus y plus z is equal to x plus quantity y plus z. Or quantity x or y or z is equal to x or quantity y or z. Okay? The dual law, which means we have addition, the dual is multiplication. Okay? Wala tayong division and subtraction because subtraction is done into complement, and division is done by shifting. No? X and y, quantity x and y and z is equal to x and quantity y and z. And is multiplication. So associativity law. Other laws, no? You have to memorize this because when you simplify Boolean expressions, you should be able to do them quickly, like 1 times 1, 2 times 1, 3 times 1, okay? 3 times 10, automatic, diba? So x plus 0 is x, diba? Or x or 0 is x. Anything ORed with a 0 is itself. X times 1 is x, no? Anything ANDed with a 1 is itself, right? You can draw the truth table. The main law, complement. X plus its complement is 1. Wow. Kasi one of them is 1 and one of them is 0. Right? So 0 plus 1 is 1. And dual law, x times not of x is 0 because one of them is x and one of them is 0. We're not sure where they are, no? But anything multiplied with a 0 is a 0. Okay? That's what we are sure of. Okay? So that's why you have x and not of x. Sometimes not of x is written this way. No? So duality. There's a duality between and or. No? So here is an example. No? Now, to compute the dual, no, of an expression, if two Boolean expressions are equal, then their duals are also equal. Now, a dual of a Boolean expression is formed by replacing ands with ors and ors with ands, and ones with zeros and zeros with ones. Okay, ones with zeros and zeros with ones. Variables are and their complements are left alone. Okay, for example, there x plus 1, the variable x is the same, no? And then plus is converted to multiplication, and 1 is 0. So if you say x plus 1 equals 1, the dual is x times 0 equals 0. Diba? Binaliktad lang. The x being a variable remains the same. The plus becomes a times. The 1 becomes a 0. Okay? Or if you do the reverse, the 0 becomes a 1. Okay. X plus x equals x. Right? So since all our variables, there's no 0 and 1, we say x and x is also equal to x. Okay? X plus not of x equals 1. So x times not of x equals 0. Variables are left the same. Ones become zeros, zeros become ones. Okay? That's how to compute the dual of an expression. Which means if you have this expression, you don't have to prove the dual. You just show that it's the dual of that expression. Now, SOP and POS are duals. Okay? Do you follow? SOP and POS are dual. So if you look at this, our variables, our expressions, a plus b plus a not b is the dual of quantity a plus b and times quantity a plus not of b. Duals ito sila. They are the same expression. which means that they come from the same truth table. Do you follow? When you say dual, they come from the same truth table. Okay. Before we proceed with this, we'll go to midterm expansion, no? Because we can do this using software. No? Do you follow? I'd like to introduce you to a software called Cedar Logic. There's so many other softwares. No? They're free. Okay, so you can download them. There's a site. Okay, ito yung download site, no? This one. Okay, you download, and then there's a video. Okay, they follow. So anyway, let's try to do our first example in Cedar Logic. How do you construct a circuit? Now, normally you can have an actual circuit, no? But you will need wires and plug boards and breadboards, no? And then you will need a power supply. We used to do that in a lab, no? In a physics lab when there was no pandemic. Okay, but now with the pandemic, we don't have an electronics lab, so we will use a simulator. So this is called Cedar Logic simulator. So you download Cedar Logic, you install, then you run it. Okay, this is like a breadboard, no? Now in Cedar Logic, you can have basic gates, all the gates, no? You can have invert gates. You can have input and output, no? You can have decorations like text, no? MOOCs, decoders, we'll discuss this, what they are. Then we have flip-flops and registers, we also will. Now the only problem is we don't have ALUs, which I don't like. Walang ALU dito, so we have to construct our own ALUs. Arithmetic logic units, no? There are others like Logisim. I used to have Logisim, but I had a problem installing Logisim in Windows 10. So goodbye Logisim. And then there's also Adafruit. There are many others. Now let's construct this expression. Y equals AB plus A not B. So we have two variables, A and B. To do a variable, we'll use a text decoration. A text decoration is just text, no? There's nothing usual. We just put a text there. Then we double click, we say this is A. Okay. We put another text, this is B. Just a label, no? Okay. And then we will put AB. We need an AND gate, AB. Okay. Now sometimes we will need a connector because we may have more than two connections. So we will use a connector. Where is that? This one, no? Invert and connect, we'll put it here. So we can connect A to and B to a connector. And then we can use an input and output. Ito, no? Okay. So we can configure. We can configure whether the input is a 0 or a 1. We follow? In this case, A and B are 0. Okay, when you want to make B1, you just click. A red means 1, so this is 0, 1. Okay, this means 1, 1. This means 1, 0. This means 0, 0. Okay, do you follow? Okay, so where did I get that? In input and output. And I also have invert and connect. Ito yung connection ito. Because without this connector, you can only make 2 connections. With this, you can make 4 connections. Okay, we'll find out why. No? First, we have A and B. So we'll go to basic gates. We'll need an AND gate. A and B. So we'll this is A and B. Take note, no? So meron tayong connection. Do you follow? Do you follow? The next connection is another AND gate, A and NOT of B. So we have A. This is our A. So take note, we can connect. And we need a NOT of B. So we can move this like that, no? We need a NOT of B. So we will need an invert and connect. So we'll need a NOT. This is a NOT, no? Pwede rin ito maliit. Anyway, it's the same. The NOT of B. Do you follow? So this is, and then we need an OR gate because we are going to implement this plus. Okay? Do you follow? consider logic. Where do we find an OR gate? We go to basic gates. We need an OR gate, and then we connect it here. Okay, they follow. Now, in an actual experiment, in an actual laboratory, you will need ICs. But yeah, we don't have ICs here, so we just use the gates. And then we will convert the output. So we'll have input and output. There's an indicator of one output here. This is an output indicator, the LED indicator. Okay, we can also use a connection, which means that if it's 0, 0, the output is 0. 1, 1. So 1, 1. So the output is 1. 1, 0. The output is 1 because 1 means red. Okay. 1, 0, 1. The output is 0. Do you follow? You get my point? You will need this because you will compute the min term and the max term, and then you will construct in consider logic. The way to check if you have the correct min term is to check the actual circuit in consider logic. It generates the truth table correctly in consider logic, then you have the correct min term or max term. Any questions so far? Okay. So, we'll not solve anything yet. Hanggang dito lang muna tayo, no? Okay. You download your CIDR logic, right? You install it already. You can construct the example that I have. Okay. We follow. You watch the video. Okay. You watch the video. And then for CIDR logic introduction. This is a play thing, no? This is a toy program, not just for students, but even for electronic enthusiasts, those who would like to assemble circuits or schematics. No, this is a schematics circuit. Okay. Any questions? Okay. So I'll upload this lecture. I will stop at this point, no? And then next meeting we will discuss actual math. Wala muna tayong math ngayon. The actual math. Okay, we'll start next meeting. But anyway, you already have a sample test, no? You already have a practice test, no? Which you will do maybe next week. It's a new message. Okay, none so far. Okay, so see you on Thursday. We'll continue. Those who haven't taken the test, please take the test now. You still have until tomorrow. And then those who need to take a higher grade to get a higher grade, please retake them. I have removed the unnecessary takes before, no? So you can, I'm sure of all of you can still retake those who have failed, no? Okay. Okay. So see you next meeting. Bye everyone. No? We stop at this point. Thank you very much.
Sir.
Bye, sir. Thank you, sir.
Bye.
Thank you,
Thank you.
sir.